Simulation of mastication movement using SolidWorks. Simulation of mastication movement using SolidWorks. In this section, we will use SolidWorks motion capabilities to simulate mastication movements. There are two types of mastication motion: chopping motion and gliding motion. The term mastication motion is rarely used in the dental technologist site. I think it is expressed as lateral movement. Why is it called mastication? It is not simply because the mandible moves laterally, but also because there are food fragments between the occlusal surfaces of the upper and lower dentition. When the mandible makes lateral movements, food fragments trapped between the upper and lower dentition are chewed and crushed. This simulates the gliding motion, one of the masticatory movements. In addition to the conventional evaluation methods, a new evaluation method for tooth alignment has been presented. In the past, when mandibular movement was made, the upper and lower teeth were evaluated to see if they interfered, slip through, contact, or glide. It is now possible to ask about changes in the proximity relationship between the occlusal surfaces of the upper and lower dentition. I think this means that one of the new methods of evaluation has been presented. Here is a specific representation. It cannot be represented as a single mass as a food fragment. We represented the food fragment as a collection of particles. We set the number of particles to 60, 100, 150, and 200. The greater the number of particles, the greater the degree of representation as an actual piece of food. However, the larger the number of particles, the longer the computation time becomes. The time required to calculate a simulation of only 1 second is about 6 hours for 60 balls, 1 day for 100 balls, 3 days for 150 balls, and 11 days for 200 balls. With this much time required, it is not possible to incorporate this simulation into daily clinical work at this point in time. I believe that simulation of mastication movements can be used for research purposes. I have tried to represent it in this video to show what it can do at this point. I do not know what kind of a particle that represents a piece of food would be appropriate. Here we have used a true sphere, an ellipsoid, and a truncated icosahedron, in the state of a soccer ball, as the particle shapes. The size of one is about 0.8 mm to 1 mm. About motion settings. SolidWorks Motion uses 9 linear motors to move the mandible. Coordinates in three-dimensional space consist of 3 orthogonal directions: x, y, and z, or length, width, and height, respectively. The movement and rotation of a particular rigid body in space can be represented by the elements of a coordinate point attached to that object, a displacement of 3 points. 3 points were set on the measurement probe attached to the front of the lips. The motion of the mandible was measured using a probe connected to the mandible. The data of the trajectory of the 3 points on that probe is loaded into the CAD. The motion of the mandible can be reproduced by exercising the related parts in accordance with the motion data of the 3 points. The probe has 3 points, each of which requires 3 linear motors responsible for displacement in the x, y, and z directions. Since there are 3 points on the probe, 9 linear motors are needed. Another method is to use only one linear motor. That method requires 3 curves and related parts to move a single point. In this case, we used the method with 9 linear motors. Let's take a look at the results right away. Conditions of the setup. The number of particles is 60 spheres, the particle shape is true sphere, the simulation time is 1 second, and the gravity is 0 meters per millisecond squared case. This simulation has 0 gravity. The particles stay in place unless an external force is applied. The impression seen in the simulation is something unnatural. The number of particles is so small that no particles are ejected even if they are bitten through to the centric occlusion. In this simulation, the calculation stopped just before biting through to the centric occlusion. The reason for this is that the particles overlapped between the occlusal surfaces and locked up instead of ejecting. This is why this part of the timeline is slightly missing. Conditions of the setup. The number of particles is 100 spheres, the particle shape is an ellipsoid, the simulation time is 1 second, and the gravity is 10 meters per millisecond squared in this case. The gravity setting for this simulation is 10. The real gravity is 9806.650, which is a much smaller value. This image is a buccal view of this simulation. Rather than the mandibular teeth pushing the particles up through the gap, we can't help but feel that gravity is causing the particles to flow down through the gap. It does not feel like chewing. I think the reason for this phenomenon is that the gravity value setting is too large. It would be better to make it a little smaller. Here are my impressions of this case. The simulation looks much more natural than the first case. The number of particles is still low enough that biting through to the centric occlusion does not eject the particles. Conditions of the setup. The number of particles is 150 spheres, the particle shape is true sphere, the simulation time is 1.2 seconds, and the gravity is 1 meter per millisecond squared in this case. The gravity setting for this simulation is 1. We reduced the gravity drastically. We increased the number of particles to 150 spheres and the analysis time to 1.2 seconds. The duration of mandibular motion remains unchanged at 1 second. The 0.2 seconds added was extended to observe the particle dispersal after the mandible reached the centric occlusion. The change in settings has been successful, and we can see how particles are ejected lingually and buccally when biting through to the centric occlusion. You can see the feeling of particles flying out of the gap with great force. It feels like chewing. I think the value of gravity could be set a little higher. Conditions of the setup. The number of particles is 100 spheres, the particle shape is a cut-topped icosahedron, the simulation time is 1.2 seconds, and the gravity is 1.5 meters per millisecond squared. This is the reason why we have changed the particle shape from spherical to a cut-topped icosahedron. Until now, we have used shapes composed of curved surfaces. I tried before to see what would happen if the particles were made rectangular in shape. The particles easily overlapped while moving, locking up and stopping the calculation in the middle. So we thought that a polyhedron composed of planes would work. In the case of a polyhedron, you can visually see when the particles rotate. The change in the shape of the particles was successful. When the food pieces were bitten through to the centric occlusion, the particles were ejected to the lingual or buccal side and the particles were observed to rotate. Another advantage is that calculation errors seem to be less likely to occur for polyhedra composed of planes. In the case of a true sphere, a computational error could occur, where the particles would be dug into the surface of the tooth. The particles are shaped like this. The plane configuration is similar to that of a soccer ball. This particle is composed of pentagonal and hexagonal planes. Conditions of the setup. The number of particles is 150 spheres, the particle shape is a truncated icosahedron, the simulation time is 1.2 seconds, and the gravity is 1.5 meters per millisecond squared in this case. The change in the shape of the particles was successful. When the food pieces were bitten through to the centric occlusion, the particles were ejected to the lingual or buccal side and the particles were observed to rotate. If there are about 150 particles, you can see in detail how the food fragments are crushed and ejected. Although we were only able to show one way in this case, we believe that the state of ejection will vary depending on the occlusal surface geometry. Conditions of the setup. The number of particles is 200 spheres, the particle shape is a cut-topped icosahedron, the simulation time is 1.2 seconds, and the gravity is 1.5 meters per millisecond squared in this case. If there are about 200 particles, it is possible to see in detail how the food pieces are crushed and ejected. A simulation with 200 particles requires a very long time, 11 days of computation time for a simulation of only 1.2 seconds. It would be faster with a more powerful computer, but even then it is unlikely to be completed in 5 or 10 minutes. It would be worthwhile if limited to research use. The computer seemed to freeze at the time of the calculation, but I waited for 11 days as it seemed to be doing the calculations. The results came out. The color of the particles is purple, unlike the previous red, but there is no particular meaning to the color.